Hello everyone, and welcome to another in the series of TerraSource Global webinars. Today's topic is Crusher Feeding 101. My name is Jack Logue, and I'm happy to be the presenter today. Today we have several items on the crusher feeding agenda. These include a little background in general feeding criteria and the various types of crusher feeders. TerraSource Global manufactures many different types of crushers, and there are different requirements for each. We'll talk about the different requirements as applies to each of the crusher types. We have a couple of different reversible crusher product lines, and we'll talk about the specific requirements of these lines. And finally, we'll discuss the consequences of poorly feeding crushers and discuss some troubleshooting. Let's start off with some general crusher feeding criteria. Most crushers like a steady feed rate or one where variations are infrequent and small. The feed should enter a crusher in a manner which spreads the wear over all the crusher components. To achieve these two criteria, a mechanical feeder is generally required. As we will see, there are some considerations and some crushers that don't necessarily require mechanical feeders. We'll get into those as we go along. There are several types of mechanical feeders. These include vibratory feeders, belt feeders, posimetric feeders. In all cases, to feed the crusher properly, the feeder should be approximately the same width as the crusher feed opening. Generally, not off by more than 6 inches total or maybe 3 inches on a side. A feeder must also have a surge bin above it to properly feed it. The surge bin acts like a means of leveling the feed on the feeder and also spreading the material over the feeder so that it can spread the material to the crusher opening. Examples of vibrating feeders include our Jeffrey Rader electromechanical and electromagnetic feeders. Vibratory feeders are volumetric feeders, but when installed with a proper surge bin to feed them, they will accurately deliver material to a crusher while properly spreading it over the whole crusher width. Another very popular crusher feeder, especially with many of our very wide crushers, is the posimetric feeder. This feeder, while also a volumetric feeder, delivers an accurate feed rate on a weight basis because of its design, which delivers the same volume every revolution of the feeder. Because the feeder must be full to work, they also help reduce dusting due to the fan action of the crusher below them. A posimetric feeder, because it delivers the same volume regardless of the material moisture, is only as inaccurate on a weight basis as changes in the bulk density of the material. Generally, feed materials don't change radically in bulk density, and so the posimetric feeder can be a very accurate feeder on a weight basis. The posimetric feeder has been a popular feeder in dusty PRB coal applications where we must crush the coal to a very fine size and we need to use a high-speed hammer mill. And the posimetric feeder, because it creates somewhat of an airlock above the crusher, prevents dusting up in the higher parts of the crusher house. Multi-duct feeders are used to match up the feeder width with the crusher width. Here we see a posimetric feeder that has 3 compartments or 3 ducts. What we do is we match the feeder width to the crusher width, and then we adjust the rate to the crusher by the speed of the feeder. It's more important to get the width correctly, and then we can adjust the speed to vary the rate to the machine. Posimetric feeders require very little horizontal offset from the crusher also, because the entry and exit points, I'll go back one slide here for you, the distance between where the material enters the posimetric feeder and where it exits is relatively short compared to some other feeder types. Another popular crusher feeder is a belt feeder. Belt feeders spread material across the crusher width and control the rate to the crusher by weighing the material on load cells along the feeder belt. Changes to the crusher rate are done by changing the speed of the feeder. Generally, these feeders have a longer horizontal offset from entry to exit point on the feeder. TerraSource Global manufactures many different crusher types, as I mentioned. I'm now going to discuss the feed requirements of each of these types and explain why the requirements differ. We're going to talk about Bradford Breakers, cage pactors or cage mills, jaw crushers, frozen cold crackers, which are single roll crushers, other roll crushers, 2-roll and 4-roll crushers, and one-way paddle and one-way ring mill hammer mills, and then finally reversible hammer mill crushers. Bradford Breakers are large, horizontally mounted rotating cylinders and are employed to crush and separate materials of different hardnesses. Most often they're used to separate rock and other debris and reduce the coal that is coming out of a mine, the run-of-mine coal. Coal being softer can be lifted and dropped and screened out, and all of the uncrushable material gets carried down to the end of the cylinder and is scooped out the end. This crusher, because spreading the material is not necessary, can be fed with a conveyor belt, and quite often they are located directly at the mouth of the underground mine where the material is coming up the slope belt and goes right into the Bradford breaker. A uniform feed rate is also not critical, but overfeeding a breaker can cause the coal to report in the reject of the breaker rather than being lifted, dropped, and screened out through the holes. So overfeeding the breaker can reduce its efficiency, although a breaker can handle overfeeding. It just will have good product report with the debris. Cage mills are another type of crusher that can be fed by a conveyor belt because the feed enters the crusher through a chute that feeds material into the center of the crusher. The material must then work its way from the center of the crusher out through the counter-rotating cages and fall out the bottom of the mill. No feed spread is required, but the cage mill does require a uniform feed rate for efficient material sizing. Let's take a look at this for a second. Material enters through a chute, comes down and into the cage mill, and then must work its way through the cages and falls out the bottom. Another shot. Here's a shot of a cage mill in the installation. The material comes down. There's the feed chute here where the material enters the cage mill and then material exits out. Your drive is back here. Your feed chute is here. Jaw crushers are another unique machine from a feeding standpoint. These crushers actually perform better when they're choke fed. Choke feeding means that the crushing chamber is full of material while the machine is operating. This provides for the maximum number of crushing strokes as the material works its way down through the jaw crusher. However, in order to provide voids or spaces in the crushing chamber to accommodate the swinging jaw when it swings forward, it's always a good idea to scalp out the undersized material before the jaw crusher. In other words, any material that's already product sized should be taken out ahead of the jaw to leave voids for the crushing action to occur. If too many fines are included with the feed, the crushing chamber will become plugged, and damage to the jaw frame can actually occur when there is no voids for that swinging jaw to close on the material. Therefore, the best feeding arrangement for a jaw crusher is something like I have shown here. Here we have a dump hopper up above to a grizzly feeder where the undersized material is screened out here before, and the oversized goes in the jaw. So what we're doing is we're taking out the undersized material before the jaw. This gives the most efficient and the easiest work on the crusher itself. Frozen cold crackers are located under rail car dumpers at power stations in cold weather areas. Their job is to reduce large frozen lumps of coal to a size that is conveyable or won't plug hoppers and transfer points. Generally, output sizes from a frozen cold cracker are about -6 inches, sometimes as small as -4 inches. Just something that can be conveyed. Most of the feed to the frozen cold cracker is material that's already been sized, maybe 2-3 inches, just frozen into larger lumps. These crushers have drives that allow them to be started under load and to operate completely full of material. A clutch coupling or fluid coupling that's between the motor and the gearbox protects the motor and allows it to start loaded. The frozen cold cracker, however, will not act as a valve. If all the material is undersized, there are no frozen lumps, for instance, that material will flow right through the cracker and would flood the takeaway belt. For this reason, in order to control the rate to the takeaway belt, a feeder is oftentimes located after the frozen cold cracker, and it can control how much is loaded onto the takeaway conveyor. This may cause material to back up into the frozen cold cracker, but as I mentioned, the drive is set up so that the frozen cold cracker can actually churn in a bed of material while it's operating. On our other roll crusher lines, both single stage and double stage machines, we require some type of feeder to control the rate and to spread the material out over the full crusher width. In primary applications, the roll crusher can be fed with a conveyor, and it's not as critical, but if the output size is smaller and it's in a secondary application, proper feeding is important to spread the material over the entire roll. Proper spread is important, but so is directing the material between the two rolls. These two factors are crucial to attaining product size or output size and capacity. Our capacity calculations are based on the full width of the rolls being used. So if only 50% of the roll width is used or the material is fed down the center of the rolls, full capacity cannot be attained. If the feed is not directed properly between the rolls, but rather is directed on top of one of the rolls, foul balling will occur, which restricts material entering the rolls and will reduce capacity. I have a couple of pictures here of poor feed situations, and you can see here the feed was concentrated in one area, probably because the material was fed by a conveyor. And you can see that only about half the roll width was actually used. Here's another photo of a poor feed situation, you can see how difficult, if this is your feed situation, it would be to make the specified output size or capacity for that matter. Keep in mind that while there is cost involved in installing the proper crusher feed system, the cost of improperly feeding a roll crusher, for example, is premature wear and replacement of these rolls, which are not inexpensive. Proper feed setup is paid for only once, but you're going to pay for a poor situation over the entire life of the crusher. We make a variety of one-way hammer mills. Some of these machines have flat-faced paddle hammers and some have ring hammers. We'll address each of those. Ring hammers, or in the case of our flex tube machines, they have a rounded hammer. Let's talk about our one-way hammer mills that use a flat-faced paddle hammer. Again, a machine like this needs the material spread over the entire rotor width so that all the hammers do equal work. And we would like to see the material in a machine that has a flat hammer enter through the center of the feed chute and directly down in front of the rotor. On our ring type machines, or where we're using a rounded hammer, what we're trying to do here is minimize the impact somewhat. We're trying to reduce what I call be inefficient in our impact by using the round-shaped hammer. These machines still require full width, again, spreading over the entire crusher width. But what we like to see with these machines is a situation where the material slides down the breaker plate really on the down running side of the crusher rotor hammers. Feeding the material down in front of the hammers along the breaker plate on the down running side reduces foul balling, since remember our hammers are kind of rounded, reduces foul balling and can reduce the vibration rather than having the material fall directly onto the rotor. This sketch here is a typical sketch that we send with our proposals that give folks an idea of where the feeder should be located above the machine in order to give the machine some velocity entering the hammer circle, because the hammers are presenting themselves so many times a second. You need to have some velocity to get the material in front of the hammers, so they needs to be dropped from some height. Think about if the material was dropped directly at the lip of the crusher, you would have a lot of foul balls. Material would have trouble even entering the crusher, and we do see that. That can be a cause of poor capacity or high power draw. And we see that when the material isn't dropped from a sufficient height above the machine. Reversible crushers are actually two crushers in one, you can think of them, because they're operated both in a clockwise and counterclockwise direction to spread the wear over two surfaces of the crusher and to keep the hammers sharp without having to turn the hammers by hand. However, because the feed drops directly down onto the rotor itself, they require some additional criteria to attain proper feed. They require a uniform feed rate, some type of a feeder to control how many tons per hour are fed to the crusher, and they also require spreading over the entire crusher width. But we have some other considerations with reversible machines. While a hopper and a feeder are required, the feeder must be located at the correct height above the crusher hopper flange so that the material has sufficient velocity entering the crusher. And also, it must enter in a vertical direction. We want a vertical chute above the crusher. No slope is desired. No matter what feed type, and here we show a posimetric feeder above the reversible machine, the feeder must direct the material down the center of the chute from the proper height so that the performance of the crusher is the same in both directions of rotation. Let's discuss height of drop and why it's important and how it's calculated. The height of drop, which is a number that we provide on our reversible crusher proposals, is the height above the top flange of the crusher from which we drop material with zero initial velocity and where it can begin its free fall into the center of the crusher opening. What we want to do is we want to have that material drop from the proper height so that we don't have trouble with foul balls and not be able to penetrate the hammer circle, but at the same time we don't want to drop from such a high height that we over penetrate the hammer circle and actually the face of the hammer is not doing the work. The height of drop is provided to the customers, and what we give them is a height above the top flange of the crusher. We do have some room inside the crusher from the top flange to the actual face of the hammer, but that's taken into account when we give the height number. The zero velocity point is generally the point where the material discharges off the feeder lip or edge. We prefer free fall with no sliding or interference with the sides of the chute, which can cause ricocheting on the way into the crusher. It's crucial that the material enter in a vertical direction so that the crusher performance is the same in either direction of rotation. You can imagine if the feed enters at an angle in this picture here, one direction of rotation would drive material back up the chute, decreasing capacity, increasing power draw, and probably increasing the product fineness, but you're going to have a shortfall in capacity. Then when you would run in the other direction, the material would be entering on the down-running side of the hammers, and you'd have poor output sizing, probably more capacity than in the other direction, but your output sizing would not be what was desired. Height of drop is calculated so that the material is impacted on the hammer face at about the center of the hammer face. If the height from which material drops is too low, the material will not penetrate the hammer circle, and as I mentioned, you're going to get foul balling or driving material back up the feed chute. If the material is dropped from too high a height, material will over-penetrate, and where the shanks of the hammers, rather than the heads of the hammers, and we design our heads to be harder than our shanks, so you'd be wearing out the shanks prematurely. The items that go into our height of drop calculation include the RPM of the crusher. The faster the RPM, the higher the height from which the material will have to fall. The number of rows of hammers. The more rows of hammers that you have, the more hammer presentations you're going to have. The less time between hammer presentations, the material will have to be dropped from a higher height than with less hammer rows. We take into account the hammer face length. How long is the face of the hammer? And what is the distance between the different hammers in the same row around the rotor itself? And to a lesser extent, the feed size to the crusher does enter into our calculations, but just to a minor degree. So we calculate the height from which the material needs to drop so that when it enters the crusher, the piece that just misses the hammer as it comes by falls a sufficient distance to be struck by the next hammer about the middle of the face. This chart here describes a little bit about what I was saying about too low of a height of drop. You're going to hit at the top of the hammers, or the hammers are going to drive the material back up. The correct height is going to put the material about in the center of the hammer, and if you drop the material from too high a height, you're going to impact on the lower part of the hammer, maybe on the shank. You can also wear out the crusher rotor. The discs also, we've seen cases of that happening. One of the things to keep in mind is that when there may be times when we want to change the speed of the crusher or the number of rows of hammers, and sometimes the restriction would be in how much flexibility do we have in the height from which we're dropping material. Sometimes that can limit what we can do to making changes to the crusher rotor or its speed if we want to make changes to the output sizing. Obviously, if we have poor feed spread over the crusher rotor, the cage can only be adjusted as close as the least worn hammer. Most of our crushers have adjustable cages that are made to compensate for wear. So it's vitally important that all the hammers wear evenly so that the cage also wears evenly, number one, but then when the cage is adjusted, the gap between all the hammers and the full width of the cage is the same. If there are areas that are worn more heavily, oversized material is going to pass through those gaps. Here's an example of a really poor feed condition, but actually one where all the material was sliding down a chute or being fed off to one side, and you can see that in this situation it's going to be impossible to maintain correct output sizing because the cage is going to hit on the left side of this photo, or excuse me, the cage is going to hit first on the right side where the hammers are most new, and you're going to have a huge gap on the left side of this rotor, and actually you can see all the way to the left there are missing hammers. A really poor feed condition. To summarize, poor feeding can affect capacity. Again, our calculations for capacity are based on the full crusher width being used and with the material entering the crusher properly. This also is how we select our horsepower. Improper entry, or where the feed is concentrated in one area, will increase power draw. Foul balling can occur when we have improper entry angle or when the material doesn't have sufficient velocity entering the machine to penetrate the hammer circle. And lastly, poor output sizing and poor parts life is a result of improper feeding. You're going to have high wear in the areas that see the most material and little wear in those areas that don't. That's all I have for today's session. As I mentioned earlier, though, properly designing and installing the crusher feed system is paid for only once, but a poor feed arrangement will cost in the operation, poor performance, high maintenance every day that you operate the crusher. So it is vitally important to us to see the crushers fed properly. Thank you all for your attention, and I'll be happy to answer any questions that anybody might have at this time. Appreciate your attention. Anyone have any specific questions about a situation that they've had or a crusher type that they've had trouble with? Feel free to sing out. Well, that's fine. Well, I appreciate everyone's attention, and thank you for joining us today. We'll talk to you soon.